Hey everyone, welcome to another episode in Physics is Fun. Today is going to be about a test dummy jumping from a plane. Let's jump into reading the question. A crash test dummy is ready to jump from a plane going a constant 243 kilometers per hour. It is on course to aim for the bullseye on the ground 1.5 kilometers below the plane. How far away should the plane be for the dummy to land perfectly on the bullseye? What is its final velocity vector? Let's draw a picture to help visualize the problem to get our components from. We have a plane, or this triangle, where the test dummy is jumping from, and a bullseye over here for the dummy to land on. The plane flies 1.5 kilometers above ground. The velocity is a constant 243.3 kilometers per hour, and being on Earth, the acceleration is negative 9.8 meters per second squared. We are looking to find the displacement in the x direction to find how far away to jump. With a picture, let's move on to the variables and split them between x and y direction. For x, the crash test dummy, or just CTD for short, has a velocity CTD initial of x equaling 243.3 kilometers per hour. Acceleration CTD of x equals 0 meters per second squared. The x CTD initial equals 0 meters, and the x CTD final is unknown, and exactly what we are looking for. The time initial is 0 seconds, and the time final is unknown as well. For y, the crash test dummy has a velocity CTD initial of y equals 0 kilometers per hour, and an acceleration CTD of y equals a negative 9.8 meters per second squared. The y CTD initial equals 1.5 kilometers, or just 1,500 meters. The y CTD final equals 0 meters. The time initial is again 0 seconds, and time final is unknown. With all the variables written, we can start looking at equations to use. Let's convert our units first for velocity to meters per second. So, to calculate the 243.3 kilometers per hour, need to convert to meters per second. So, to convert kilometers, multiply the top by 1,000 meters over 1 kilometer. To convert from hours to seconds, there are 3,600 seconds in an hour, so take 1 hour divided by 3,600 seconds. This should cancel out the kilometers and hours to leave us with meters per second. So calculating, we get 67.573 meters per second. Let's write that in for the velocity now, changing from the kilometers per hour to 67.573 meters per second. Now for our equations, we are looking for the distance in the x, but cannot quite solve it yet as we need a time final. So with the y components, we can find the time using y final equals y initial plus velocity initial times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. With the equation, we need to find time, so it's time to calculate. With the equation, y final equals y initial plus velocity initial times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared, we need to solve for time final, so subtract y initial from both sides and cancel on the right to get y final minus y initial equals velocity initial times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. Our velocity final in the y is 0, and so is the time initial, so cross those out the equation. This leaves just negative y initial equals 1/2 times acceleration times time final squared. Divide both sides by 1/2 times acceleration and cancel on the right to get time final squared equals negative 2 times y initial divided by acceleration. Now square root both sides to find time final as square root of negative 2 times y initial divided by acceleration. Now we can plug in to get time final equals square root of -2 times 1,500 meters divided by -9.8 meters per second squared. It becomes positive, and the m cancels, and the s squared goes up, and calculates to a final answer of just 17.496 seconds. So it takes 17.469 seconds for the dummy to reach the ground. Let's write that in for the time final. With the time, we can now calculate the x distance we need. The x velocity is constant, so we can use the simple velocity average equation to find the displacement. Velocity average equals delta x over delta time, or x final minus x initial divided by time final minus time initial. Let's calculate. Rewrite the velocity average equals x final minus x initial divided by time final minus time initial. And both x initial and time initial are 0, so cross those out. And to solve for x final, we want to multiply both sides by the time final to cancel on the right side. We are left with x final equals velocity average times time final. Plugging numbers in, we get the x final equals 67.573 meters per second times 17.496 seconds, crossing out the seconds to get a final answer of 1,182.444 meters. So the dummy needs to jump 1,182.444 meters away from the bullseye. Let's write that in the variables. And let's also add the velocity CTD final of x equals 67.573 meters per second, and we need the velocity CTD final of y to find the vector resultant. Remembering our coordinates of x and y are at ground level, and the resultant vector gets placed here. We need to find the velocity final for y direction, so we can use the equation velocity final squared equals velocity initial squared plus 2 times acceleration times y final minus y initial. Let's calculate. Rewrite the equation to get velocity final squared equals velocity initial squared plus 2 times acceleration times y final minus y initial. And solving for velocity final, we just have to square root both sides. This leaves velocity final equals square root of velocity initial squared plus 2 times acceleration times a y final minus y initial. Let's plug in numbers to get velocity final equals square root of 0 squared plus 2 times negative 9.8 meters per second squared times 0 minus 1,500 meters. This equals square root of 2 times negative 9.8 meters per second times negative 1,500 meters. This calculates to square root of 29,400 meters squared over second squared, which gives the final velocity in y direction to be negative 171.4643 meters per second. Let's write that in for the velocity CTT final of y. With both x and y velocity components, let's find the final vector, and the resultant vector goes here with this theta angle. The equation for resultant vector equals square root of velocity of x squared plus velocity of y squared. Let's calculate. Rewrite the equation. Resultant vector equals square root of velocity of x squared plus velocity of y squared, and plugging in now to get square root of 67.573 meters per second squared plus negative 171.46 meters per second squared. This calculates out to the final resultant of 184.3 meters per second. Along with magnitude, we also need direction. So to find direction, we need tan of theta equals opposite over adjacent, or the velocity final of x over the velocity final of y, in this case from our triangle drawing. Solving for theta is the tan inverse of velocity of x over velocity of y. Plugging in, we get theta equals tan inverse of 67.73 meters per second divided by negative 171.46 meters per second. This calculates out to a final angle of negative 21.5 degrees. With both magnitude and direction, our final resultant vector is 184.3 meters per second at 21.5 degrees off of the negative y-axis. We have found the displacement for the crash test dummy to hit the bullseye and found he hits the bullseye at 184.3 meters per second at negative 21.5 degrees. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching. Hope you come back to learn more exciting material, and see you next time.